Okay, here is your introduction to sequences, our next unit in your IB math class. Do want to point out that if you need to pause this recording at any point in time to jot down the information, you should do so. Our first definition of a sequence, since that's our brand new unit and you may not have ever heard of it, the definition of a sequence is, of course, any or actually an ordered list of numbers defined by a rule. It's very important that there's a rule. The numbers in the sequence themselves are called members of the sequence. A sequence that continues forever, infinite, and a sequence that terminates or comes to an end is called a finite sequence. So again, a sequence is the ordered list of numbers that have to be defined by a rule. So here is an example, and there's some writing on here that I will attempt to erase for us. So it doesn't get in our way. I've been having some weird problems with this. Well, hopefully it doesn't continue. So if our sequence starts with a 4 and our rule is to add 9, 4 would be the first number. That would be our first term. The second term would be, that's what I'm trying to get not to happen. The second term would be 13. The next term would be 22. And the fourth term would be 31. If we were adding 9 each time. And part of this is important because this is considered your first term, your second term, your third term, and your fourth term. So these are the term numbers. And up here is the actual value of the term. So similar, we start with 2. And we will multiply by 3 each time. So the first term would be a 2, so that'd be my first term. If I multiply by 3, I would get 6. That would be my second term. If I multiplied that by 3, I'd get 18. That would be my third term. And if I multiplied that by 3, I would get 54. And that would be my fourth term. So this is going to be one where you try, you're going to pause it, you're going to try it, then you're going to unpause it, and you're going to look at the answers. So pause it now, and unpause it. These are what you should have gotten for your terms. Again, 45, and you subtract 6 each time, that's your rule. Part B, 96, and you divide each time by 2, that's your rule. And that's all there is to it in that particular sequence. So again, a sequence is a list of numbers that follow a rule. These, if they were to stop here, would be considered terminating or discrete, but I could keep subtracting 6 forever, and that would be considered infinite. So there are many ways to describe a sequence. In this case, I have a nice little picture over here with a bunch of bricks listed by the row that they're in. So we could start by defining this little scenario. We could say that the number of bricks is per row. We could call that, and I guess I'm just going to leave that there, U with a little subscript for an N down here, U sub N. This is going to be notation you're going to see a lot in a minute, and I do not want to change that for us. So the number of bricks could be described by U of N, and N could be our row number. So we have a row number, and we have U sub N, and again, I do not know why that's doing that. So if I come over here and write U sub N, I could label this as 3 bricks in the first row. It looks like 4 bricks in the second row. And it looks like, if you count them, 5 bricks in the third row, etc. And this would be U1, U2, and U3. So if we are to list our actual terms, U1 would equal 3. Sorry about that, U2 would equal 4. U3 would equal 5. So we're just listing our terms. If I wanted to use words, I would say that this is going to be a little bit generic, but top or first row has 3 bricks. I'm going to call those B's, 3 B's in it, apostrophe. And then our rule would be looks to me like for each row we add 1 brick. And if I wanted to make an explicit formula out of this, and that just means writing an equation, and that's what we're going to kind of get used to doing. My formula would be trying to base this value over here on this number here. So if you look at 3 as it relates to 1, 4 as it relates to 2, and 5 as it relates to 3, it seems to be that it's just whatever this number is plus 2. So my formula could be just n plus 2. So whatever row I'm in, I seem to have 2 more bricks. So that's sort of our explicit rule. That's a plus, not a multiplication sign. If I wanted to graph this thing, which I totally want to graph right now, you notice our first row has 3, so I could put a dot there. Our second row has 4, if I remember correctly. And so if I go second row 4, third row has 5, and it looks like it's going to continue going and continue up this pattern. And in row 0, it appears as if I would have 2, but and again, this looks like it might be a line, but it doesn't make sense to have a first and a half row. So even though it looks like I would be able to connect these with a line, this is what in math is called discrete. I'm going to write that word down. Because I can't actually, it doesn't make sense for me to fill in all the fractions in between these, what we call our whole numbers, our natural numbers over here, which is again why that n here we called n, that n stands for the natural numbers, and u sub n is the term that matches with that particular natural number. So we do have to look for some new notation. And this is the new stuff that you will start to see. In particular, your formula sheet is going to use this guy right here, and we've already used him. But again, these could also represent the general nth term in a sequence as well. So n is generally termed as 1, 2, 3, 4, etc. This dot, 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 because it could keep going. And again, this n stands for natural numbers, our basic counting numbers. And that would be this u of n that would match for this would represent the actual value of that term. So you would be matching up a value with like your counting numbers. So we're going to do an example. Here's a rule that we have. It generates this sequence. But really what's happening is we're taking these numbers right here, these n's, and we are inputting them into the rule. So again, you can think of these as your inputs. And once they go into the rule, which every sequence must have, they will spit out an output. And this would basically be u of 1. Don't know what's going on over there. I apologize for that. Again, this program is driving me nuts. That would be u of 2. This would be u of 3. The 7 would be, etc. So put in n1, if I put it right in here, quick example, I follow the rule, I would get 2 times 1 is 2 plus 1, boom, gives me 3. If I put in a 2, I'd have 2, plug in the 2 into my rule, 2 times 2 is 4, 4 plus 1 is 5, and that would be U2. So that is how those work. Apparently this program has gotten to be smarter than me because it's automatically changing everything to the stuff I don't want it to be. So what that means algebraically, and you will see this a lot, and you do need to get used to it, is you would have your first term being 1, and the output would be U1. When you put in 2, you would get your second term. Again, this is your term value, this is your term number. If you put in your third term, third value would give you your third term. So an example a minute ago, we had 1, and I believe it gave us 3. We put in 2, the second term was equal to 5. The third term was equal to 7, etc. So now we're going to actually be given a rule here, and we're going to find the term. So this part A is asking for, it wants to know what is the first term in the sequence by that rule. So if I literally plug a 1 in here, and I'm going to erase this in a minute, that means I also have to put a 1 in there. And so I would do 3 times 1, which is 3 minus 2. So the first term would equal 1. If I want to find U of 5, which is the fifth term, I would put a 5 in for n. And I would have 15 minus 2, which is 13. And if I want to find the 27th term, is that crazy? I would put 27 in for n, and I would have to know what 3 times 27 is, which is 81, and 81 minus 1 is 80. So this would be the 27th term, and we got it by plugging the 27 in. Again, pause this thing if you need to. All right, you're going to try this. This is a different type of function. This is has exponents up here, so it doesn't matter. You plug 1 in where there's an n, calculate what it is, and it gives you your term value for these particular values in this sequence. This is your rule up here. So I'm going to pause. You're going to pause it, and you're going to try this, and then you're going to check your answers. So now pause and unpause. These should be your answers. I think they're right. I don't know. Actually, I do. Okay, moving on. Here we go. This wants us to evaluate the first 5 terms in the following sequence. So like fancy notation would mean I would have U1 equals, and I put a 1 in here, which would give me 2, plus 11 is 13. The second term in this sequence, I'll put a 2 in here. 2 times 2 is 4. 4 plus 11 is 15. And I would do the same thing with 3 as soon as I keep fixing this. And it wants us to do 5 terms, so this is only the third term. Put a 3 in there, I get 6. 6 plus 11 is 17. You will probably notice that there's a trend here, so I'm going to now actually shortcut this because my first term, or each of these seem to be going up by 2, so I'm going to guess that this would be 19, and the fifth one I'm going to assume would be 21. 1, 2, 3, 4, 5 terms. We want to do the same thing over here. I'm going to change my color. I'm getting a little bored with the green. This again is a slightly different rule. My terms are going to go in as exponents. So my first term is going to be 3 times 2 to the first, and 2 to the first is 2, so that would give me 6. The second term, I'm going to put a 2 up here, and 2 times 2 is 4. 4 times 3 is